Hi guys, and welcome to another video, and today we're going to be looking at derivative graphs. And the question that I want to look at is the question from the November 2010 paper 1. And in this particular paper, question 9 says the graphs of y equals to g prime x equals to ax squared plus bx plus c. So they're giving us the derivative graph sketched. Unfortunately, they never give us the equation. And h of x equals to 2x minus 4 are sketched below. The graph of g prime x equals to ax squared plus bx plus c is the derivative graph of a cubic function g. Remember that the derivative graph of a cubic function is a quadratic function. Right? The graphs of h and g prime have a common y-intercept at e, c minus 2 and 0 and d 6 and 0 are the x-intercepts of the graph of g prime. A is the x-intercept of h and b is the turning point of g prime, and AB is parallel to the y-axis. So AB is parallel to the y-axis. So let's just go there. Just a little bit about derivative graphs. What do we understand about derivative graphs? Well, firstly, remember derivative means gradient. Okay, so the gradient of your function g. So this represents the gradient of your cubic function. So as you can see here, your cubic functions now will have a positive gradient here. Okay, so that means g prime x will be greater than 0. As you can see from your function above the x-axis means greater than 0. Here g prime x is less than 0, and here g prime x is greater than 0. What else do we know about derivative graphs? Well, we should know that the x-intercepts of the derivative graph is the x values of your turning points of your cubic function. Okay, and also the axis of symmetry, or the turning point of your derivative graph, is going to be the point of inflection of your cubic graph. So you can actually work that out. So remember, now how do you work out point of inflection of your cubic function? You'll take the x values of your turning points, which is minus 2 plus 6, and average it out. So that will be x equals to minus 2 plus 6 is 4 over 2 is 2. Okay, so 2 will be the point of inflection of your cubic graph. Alright, so that's just a few things that we need to know. The other thing that we need to know is that, look at here, okay, minus 2, remember now minus 2 goes from a positive gradient to a negative gradient. So from a positive to a negative. So this was your function g, and if it goes from a positive to a negative, then that means that will be your local maximum. If it goes from, as you can see here, from a negative to a positive, from a negative gradient to a positive gradient, from a negative to a positive, that will be your local minimum of your cubic function. Alright, now I'm sure all of these questions will be asked in this particular question. So let's go and answer our questions. It says write down the coordinates of E. E is the y-intercept, and we are given the straight line graph, and will tell us that the straight line graph has a y-intercept at E. So basically they share a y-intercept, the derivative graph and the straight line. So by inspection we can see that coordinates of E will be 0 and negative 4. So let's just pull that in the graph, 0 and minus 4. And let's go write that down, 9.1. So E is 0 and minus 4. 9.2. Determine the equation of the graph of g prime in the form y equals to ax squared plus bx plus c. 4 marks. Now remember that we already mentioned that the derivative of a cubic function is a quadratic function. Basically what we are doing here is we are going to be finding the equation of the quadratic function. Okay, so the equation of our parabola. What do we have? We've got the x-intercepts, which is minus 2 and 6, and now we've got the y-intercept. So we're going to be finding the equation of a parabola where we have the x-intercepts, or the roots, and the y-intercept. So we need to use this particular formula. Y equals to a into x minus x1, x minus x2, which is equal to, now remember that x and y is your point. So x and y will be your point, and the point that we're using over here is going to be the y-intercept, which is going to be e0 and minus 4. So that point will be e0 and minus 4, and x1 and x2 is the x-intercepts of our derivative graph. So minus 2 and 6, so that will be x1 and that will be x2. Right, so let's now substitute. So substitute, we're going to solve for a. Minus 4, that's a 0. What's x1? x1 is minus 2, so that's going to be minus 2. Minus 2 is plus 2, and 0 minus 6. 0 minus 6. Now let's see what we get. So we got minus 4 equals to 2 times minus 6 is minus 12. So that's minus 12a. So therefore now solving for a will give us a equals to minus 4 over minus 12 is 1 over 3. Minus 4 over minus 12 is 1 over 3. So let's now complete this question. So therefore the equation for g prime x will equals to 1 over 3 to x. Let's see what we got here. X minus x1, so that's x minus minus 2 is x plus 2. Alright, so we're going to resubstitute now our roots, x plus 2, x minus 6. So now when you're finding the equation of the parabola, you're going to substitute your a value and your roots only. Okay, and now you're going to open out the brackets. So it's going to be 1 over 3 into x squared plus 2x minus 6x plus 2x minus 6x and minus 12. Alright, so remember x times x is x squared minus 6x plus 2x minus 12. So 1 over 3 to x squared, that will be minus 4x and minus 12. So now let's take 1 over 3 into the brackets, and we'll be left with 1 over 3x squared minus 4 over 3x, and 1 over 3 times 12 will give us 12 over 3 is 4, so that's minus 4. So we can conclude that the function g prime x is equal to 1 over 3x squared minus 4 over 3x minus 4. Remember, minus 4 is the y-intercept, so everything looks right. Okay, now let's look at the next question. Write down the x coordinates of the turning points of g. So the x coordinates of the turning points of g, we've already answered that, will be the x-intercepts of your derivative function. So the x coordinates of your turning points of g will be x equals to minus 2 and x equals to 6. So for that question there, and that is 9.3. So for 9.3, that will be x equals to minus 2, x equals to 6, x equals to minus 2. Once again, remember that the x-intercepts of your derivative graph are the coordinates of your x values of your turning point cubic function. Alright, write down the x coordinate of the point of inflection of g. So how do we get the point of inflection? Besides finding the second derivative and equating to 0. Well, we could just find the second derivative here and equate to 0, right? But another way of doing that is to average out the coordinates or the x coordinates of your turning points. So you can just very well say minus 2 plus 6 over 2 will give you the x value of the point of inflection. So therefore, the point of inflection will be minus 2 plus 6 over 2. So that's 4 over 2, which is 2. So therefore, x equals to 2. Okay? Now, let's look at the last question. Explain why g has a local maximum at x equals to minus 2. Now, once again, I've explained that. As you can see, your local maximum will go from a positive gradient to a negative gradient. So it goes from g primed x greater than 0 to g primed x less than 0. So all we need to say is that g primed x greater than 0, so it goes from g primed x greater than 0 from a positive gradient to a negative gradient at your local maximum. Okay? And there's a local minimum, goes from a negative to a positive gradient. So writing that solution down, 9.5. So 9.5, so let's say, for local max, which is at x equals to minus 2, g prime x, the derivative, it goes from a positive gradient to a negative gradient. So it goes from a positive gradient to a negative gradient, and if we want to explain that, we can explain it like so. So if this is g, remember now that it goes from a positive gradient, positive, to a negative gradient. And therefore, your max is at x equals to minus 2. So that's why that is a local maximum value. Alright, explain why g has a local maximum at x equals to minus 2, because it goes from a positive gradient to a negative gradient. Now, what if they are to ask you to sketch the cubic function, to sketch g? Well, it's important for us to know how to sketch g. So let's look at this particular function again. To sketch g, we'll have to start off by looking at the x values of your turning points, which is minus 2, 6. So let's have a look at that, right? So all you need to do is, well, if you want to sketch the cubic function g, right, what we're going to do is, okay, we don't need the y-axis. What we're going to do is we're going to draw a broken line like so at our x values of our turning point. So we got 1 at negative 2 and the other turning point is at 6. Remember, once again, the x values or the x-intercepts of your derivative are the x values of your turning point. Now what's happening here between minus 2 and 6? Remember that this particular function or your derivative or gradient is less than 0. So it has a negative gradient, and we already wrote that down. So it has a negative gradient there. So therefore, for negative gradient, remember that your line will slope in a direction like so. So the line slopes in that direction for negative gradient. Therefore, now completing your function, g should look like this. So your function g should look like that. Okay, so therefore you can see once again that you got your local maximum at x equals to 2, right? In fact, minus 2 is your local maximum. We don't know what the y value is because we don't know the equation of g, and your local minimum will be at 6 and whatever that y value is there. Okay, so that's how you actually draw the cubic function from the derivative graph. Learners, if you haven't subscribed already, don't forget to subscribe to JL Maths and check out all the videos on my website, which is jlmaths.com. And I'll catch you in the next video.